Today we are going to build this, a 3D rotating ASCII cube in the terminal. I will start by discussing all the problems we are going to face and how to solve them. And then I will implement the solution. This video is going to contain quite some math. I will try to explain as much as I can, so hopefully I'm not going to lose too many people. Alright, we got a lot of things to do, so let's start. So let's start by thinking about the different spaces we need to deal with. We got a screen. We got our computer screen, which I guess will be represented by our terminal, and our terminal can display some characters. Okay, here's some characters. And we want to give each of these characters a sort of like name or coordinate. So what we can do is say that, well, we got two axes, an x-axis that goes from left to right, and a y-axis that goes down. The top leftmost character has the position 0, 0. It's like the origin. Okay, this is 1, 0. And this one is like 0, 1, 2, 3, 4. Like 0, 4. So this is a flat 2D space. And we want to display some 3D cube on it. But the cube is not 2D. It lives in the 3D space. And whenever we deal with 3D objects or 3D space, we have a choice to make. Because there's two different ways to describe 3D space. And this comes down to handedness. You can imagine someone, okay, imagine someone here, is facing you. And he has his right hand, like this. This is his thumb, this is his index, this is his third finger, and then the two older. So this is his right hand, and he has a left hand too. This is his thumb, his index, third finger, and the two other, we don't care. Up, so he has two hands, okay? This is his left hand. And each of these three fingers represent an axis. So the thumb is the x-axis, the index is the y-axis, and the third is like the z-axis. And so here we have two different ways to represent some 3D space. So x, y, z like this, or like this. And so these two looks quite similar, but they are different. You know, like your hands looks very similar, but they're actually very different. And there's no way to turn like your right hand into your left hand. And so these two ways of describing space are not equivalent, because you can describe some object in this space, and if you take the same coordinates, the same points, they will look like the image in the other coordinate space. You know, for example, in 2D space, it's different. We don't have this problem in 2D space. In 2D, you have, for example, only one way to describe the space. And you can pretty much put x and y wherever you want. Because the same point in using this 2D plane, or that one, for example, you put y here and x here. And if you say, oh, I got like this point at position 2, 2, 1, this is 2, 1. And then I will try to be about the same space. This is 2, 1, 2, you know. We start with x and then y. And it doesn't look like it's the same point, but it kind of is. And you're probably not convinced by this, but let me show you something, okay? Here, my claim is that these two coordinate systems are equivalent because what I can do is flip this one and then rotate it, and then I end up with like x and y, and I got this point, And then if I did it properly, you know, this should kind of correspond to the same point, okay? So if you can rotate, like flip and move around the coordinate like system, then it's the same, okay? That's not the case in 3D. You can't like rotate this one into this one. So we have a choice to make. And for this video, I'm going to take this right-handed coordinate space. And in this coordinate space, so x, y, and z, I'm going to define a cube. And my cube is going to have its center at the origin. And I'm going to try to draw a cube. And I'm going to have my 3D cube like this. So the center of my cube, like inside the cube, will be the origin, and then it will go into like, this will be like 1, -1, 1. This point will be, so it's -1x, 1y, -1z, and this one is -1, 1, 1. So all of the vertices, so all these points here are going to have some combination of like 1 and -1. And so the information I need to represent my cube is really just this 1, 2, 3, 4, 5, 6, 7, 8. You know, it's like ding, 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 ding. I will need to store these 8 like points. Okay, now I'm going to talk about something very quickly. In this video, I'm not really going to make a difference between points and vectors, okay? Points and vectors. There's a difference, but in this video, I'm going to pretty much call everything a vector. Because if you think about it, let's say in a 2D plane, so you got like x, y, you will express any point by some value of x and y. And you can express any vector using like an arrow. And this vector that starts at the origin and like point to this point will also be expressed as xy, you know, xy. So to me, points and vectors are kind of the same thing, you know. They're not, but you know, it's like this IQ meme, like, no, you can't call points and vectors. They're not the same. They're not the same. It's like, yeah, whatever. Nobody cares. Okay. Okay, so now that we know how we are going to represent our 3D space, how a cube is going to be represented, let's try to put the two together. So let's say this is our screen or our terminal. And so we said that this is the top left corner, and this is going to be the origin, and we got the x-axis that goes to the right and the y-axis that goes down. Then the z-axis is going to go inside the screen, z. You're sitting in front of it, and so the positive z are inside it. We got some 3D space, but we only have a 2D screen. So how do we like transform this 3D cube into some 2D image on the screen? So we do this using what we call a projection, and there are several types of projection we can use, but I'm going to use perspective projection. So the way it works, forget for a moment that I told you that the origin is on the top left corner. Okay, forget that this origin. To understand perspective projection, let's imagine that this is your screen. Okay, and you are looking at your screen. This is your eye, and you're looking at it straight in the middle. Okay, And this line is actually going to be the z-axis or the z-axis. You are going to have, let's say this is the y-axis. Let's say it goes down. And the y-axis is like pointing toward us this way. Bing. But let's just focus on the y values for now. And so, well, your eye, and I forgot to say, but your eye is going to be the origin. Okay, this is the origin. 0, 0, 0 in 3D space. And so we can imagine that we have our cube in this space. Okay, so this is our 3D cube inside our screen. And what we want to do is display the 3D cube into this 2D plane. And the way it's usually seen is like there's some light, okay, this is like the sun, and one of the light beam is going to hit this cube, and then it will hit like one of the corner, one of the vertices, and it will draw a sort of straight line inside your eye. And so then this corner is going to hit the screen at this position. And so what we want to know is this size, this position, and let's call it y prime, knowing that we know this y. You know, we know this position of this cube, of this vertex. So this y is equal to this length from this like z-axis to the y. And when you look at this, you should see that it forms some triangles, like two triangles. There's a small one here and a bigger one there. And something you should know is like this rule of similar triangle, or the like Thales theorem. So what does this rule tells us? Well, we know that this length, so what we are looking for, this like y prime over this length, which is y, is equal to this distance, so from our eye to the screen, and we are going to say that it's 1. So 1 over this distance. And what is this distance? Well, it's the z value of this vertex. You know, this vertex has some like x, y, z coordinates. And so this is the z value. And so the y prime we are looking for is actually equal to y divided by z. And that's all we need to know to be able to print the different vertices of the cube on the screen. And it's actually the exact same thing for the x value. You know, here we were looking like straight up this way. But if we're like looking like this is from the top, you know, this is our eyes looking like this, and this is the x plan. Then we end up with the same situation, but then we just have to replace and say we have x prime is equal to x divided by z. So that's pretty much all we need to do to transform our 3D cube into a 2D object. Hopefully that makes sense. So if I come back to what I said previously, we got our 2D screen. So we got our terminal, and we said the origin is here in the top left corner. We got x and y, x, y, and z. And so then we said we are going to build a cube which has the origin as a center. So it's going to be like this, okay? And the thing we need to do is push it inside the screen, and then we will project it into almost like a virtual screen, so that we end up with some images, some points in this 2D plane. Okay, so we are going to push this cube inside, and then we're going to project to have a 2D image. The thing is, here we are going to get some like values, like all these values that are not actually going to have some real values that are not on the screen. I mean, we're only going to actually project the vertices, so, but just think it as like some 2D points. Okay, we are going to end up with some 2D points. But some of these 2D points are not going to have some like actual value that we can display on the screen. They are going to have some negative value. So once the projection is done, we will push them to the middle of the screen. To just recap quickly, we have our screen, our 2D screen. We're going to say the origin is the top left corner with X, Y, Z. Then we kind of align our cube. Then we push it. Then we will project it like this. And then we are going to push everything in the middle. Okay, I hope it makes sense. But before doing projection and pushing everything in the middle, we need to do a few things. So the first thing we need to focus on or talk about is rotation. Rotation. We want our 3D cube to rotate. And so how do we do this? The way I like to think about rotation is using linear algebra. Let's focus on a 2D plane for now. And we got an x-axis and a y-axis. And you can kind of describe any point on this plane using some vectors. And so this vector can be expressed with some value of x and y. But the way we can think about this vector is by introducing some basis vectors. So let's call this one E1 and this one E2. And E1 can be seen as 1, 0. So you go to the right by 1 and up by 0. And for E2 is, well, 0, 1. And so x, y, or let's call this vector v, v can be described as x times E1 plus y times E2. Or if we write this using the matrix notation, we can put like 1, 0, 0, 1. This is E1, this is E2 times x, y, which will just give us x, y. Okay. Thing is, this is useful because if we actually rotate these two basis vectors, so E1 and E2 by some angle theta, and that's the same here and here, same angle, then we end up with some like E1 prime, I guess, and E2 prime. And if we take the same value of x and y and we say x times E1 prime plus y times E2 prime, we're going to end up with like some vector v prime, which is going to be this vector but rotated by this same angle theta. Which means that if we can describe these two new vectors, E1 prime and E2 prime, then we can express any rotation of any vectors. Can we express these two vectors? Yes, we can. And it's not complicated. It's not too complicated. So we got this vector, E1 prime, which is the result of rotating E1 by some angle theta. here we know that the length of E1 is 1, so the length of this one is also 1. So the hypotenuse of this triangle, if we make a triangle here, is 1. Which means that this length here is equal to cosine of theta, and that length here is equal to sine of theta. So E1 prime is equal to cos of theta sine of theta. And it's the same idea using for E2. So E2 prime, and then here on the x-axis, the difference here is that we have some negative values. And so what is this length? Well, it's equal to that one, which is the sine of theta. And that length here is cos of theta. So E2 prime can be described as minus sine of theta and cos of theta. And so if we put this in a matrix, we got cos theta sine theta minus sine of theta cos of theta. And if we multiply any value of x, y, then we will get the vector, this vector, rotating by some angle theta. I hope that makes sense, but that's pretty much how I'm going to express rotation. But that was rotation in 2D. The way we're going to do it in 3D is imagining that we have this. So we got x, y, z. We are going to fix some axis, and we're going to say we're going to rotate around one axis. So around x, around z, or around y. And so to describe rotation in 3D, we're just going to say, well, one of our coordinates is not going to change, and we're just going to rotate around some axis. And so we are going to have 3 ways to rotate around x, y, and z. So I'm a little bit too lazy to write about it. So I'm just going to show you what we end up with. It's like this 3 rotation matrix, okay? And we are going to use this knowledge to implement our rotations. Let's recap a few things. So we got our screen. We got the origin, we got our x, y, z. And so because we've described our cube as a cube around the origin, it will appear like this, okay? And so the first thing we're going to do is do the rotation. So we're going to rotate this cube around the different axes. And so it will end up in some configuration. We're going to end up with like a rotated cube, say like this, for example. And then we are going to push it inside the screen. Okay, whatever. But there's one thing you need to do, which is because we describe this cube only using some value of 1, -1, then our cube is going to be very small. So we need to scale it. We need to make it bigger. And so usually what you do is you have the different points, the different corners, the different vertices of your cube. So let's say this one is like 1, 1, 1. And so what you do is you multiply all of its components by some scalar, by some like number, like k, okay, some value. We could say, oh, we're going to make it 5 times bigger, so we just multiply everything by 5. That's what you should do. The problem here is that if we do this, we're going to have a problem. And the problem is that the terminal is very limited. For example, in my terminal, I can only display about like 200 character by like 50, something like this, okay? Which means we don't really have that much value. And so we're not going to scale all of these components. Because if I go back to the like projection schematic show you, so you got your eye, you got your z-axis, all right, and you got the screen. But my screen, like y, is going to be limited to like 40 values. And so if we scale the cube, we are going to end up with some pretty big value of z, you know. And so what's going to happen is that if we project the different values, different points, then they're pretty much going to end up very small and hitting the same cell on the screen, which means we're not going to see anything, okay? So instead, what I'm going to do is I'm going to rotate the cube. So we're going to have a small cube. We push it inside the screen, and then I'm just going to scale the X and Y component. So we're going to have something like this, you know, it's going to be like, and this actually going to appear much further on the screen, and then the faces are actually going to be big enough on our screen so we are going to be able to see them. Okay, I hope that makes sense. But you know, if we also scale the Z value, then they get very close, and because we divide our X and Y by Z, then these numbers get very small and they get displayed on a tiny portion of our screen. So that's why I'm going to scale only X and Y and not Z. And it's not really a problem because we only have one object, okay? Okay, I hope that makes sense. So we know about our 2D screen, about our 3D object. We know about projection, about rotation, about scaling, about pushing the cube inside the screen. Well, now I guess it's time to think about how to actually draw the cube on the screen. You know, here everything we talked about actually only involves the vertices, but the corners of the cube. And so after all of this, all right, we're going to end up with like our screen, like this, x, y, our screen, and some value of the different like vertices of our cube. So we're going to end up with something like this, for example. And what we want to do is actually draw and fill the faces of the cube. So how do we do this? So first, the way I'm going to draw or fill the faces is by drawing some horizontal line. So we'll go line by line like this and draw this, and this, line by line. That's how I want to do it. And it turns out that there's no really easy way to do this, to my knowledge. And so we're not going to draw like squares or rectangles because, I mean, look at this. Let's say we have some rectangle that is kind of tilted. And the thing is, there's like 3 different areas, like 1, 2, 3 to draw, because you see how the direction changes, you know, they change like 1 and then like this one change here, so you got this way and then this 2 goes down. Like, you know how this forms some lines and the direction changes. You know, change 1, 2, and these 2 have different directions. Okay, so there's 3 things we need to draw, and that's a little bit annoying. So instead, we're going to simplify the problem a little bit, but not that much. So instead of drawing rectangles, we are actually going to draw some triangle. You know, we can divide our faces of our square by using some triangles. So here we have 2 triangles, 1, 2. And so we are going to describe our cube using some triangles too. Okay, so here what you have to remember is that drawing rectangle is a bit annoying. It's a bit annoying. So instead of drawing rectangle, we're going to draw triangles. And triangles are not much easier to draw, okay? But they're a little bit more easier, and if we want to extend what we're going to build to different shapes, like if you want to draw some like pyramids, I don't know how you say it, then drawing triangles is going to be the way anyway. Or if you want to draw some sphere, then using triangle is going to be the way to do it, okay? So instead of going into some fancy weird thing of trying to draw some rectangles, let's just go directly and draw triangles, okay? So this means we need to do several things. One is we need to represent our cube, the cube we draw, with more information. You know, I said we are going to store like or use the vertices to represent the cube, but here we are also going to use, or we are going to define some like triangles, okay? And we're going to split each of the faces of the cube into some triangles. And so actually, the first time I was making this program, I drew this little diagrams, I guess. And so I'm going to give each of the vertices, each of the corners a number. So 0 to 7. And then I'm going to organize the triangle by listing the different vertices. Okay? Okay, I hope that makes sense. And the way I'm defining this triangles is going to be important. I'm going to talk about this very quickly, okay? But so keep in mind that, I guess, whatever I'm trying to say. Now let's focus on drawing triangles. Let's draw some triangles. This is our screen with our X and Y axis. And we are going to get some points. We're going to get 3 points, let's say like this. And these 3 points are going to form some triangle. So how do we draw triangles? So how do we fill triangles? Well, what we want to do, and like I said, I want to draw some like horizontal line, which means that I want to know the starting position and the ending position, you know. And we need to be able to go line by line and change the value of the start and the end of this position of the line, you know. So we're going to increment 1, 1, 1, and then x beginning, I guess I can call it like this, and x end. We are going to like change their value. The thing is, you see, the beginning is going to kind of increment, but the end position is going to like increment and then decrement. I guess the easiest way to deal with this is to actually split this triangle in 2. So the first task we'll have to do is to like split this triangle into 2. This one and that one. And if you look at them independently, we are going to have one triangle that looks like this, and one that looks like this, right, whatever. And that one has a flat bottom, okay, a flat bottom, and this one has a flat, and that one has a flat top. Okay, so now we have 2 triangles. Flat bottom, flat top. Okay, I'm back for action. Wave 2. Action is coming. So. So we have our screen here. And we are going to be given 3 points. Okay. So let's say like this. like this and like that. Okay. Boom, boom, boom. And this is going to form a triangle. We are going to give each one of these points a name. So let's call it V0, V1, and V2. Actually, we want these points to be sorted by Y value. We want the 0 to be the closest to the origin, and V2 the furthest. And so the first thing we want to do is split this triangle in two. So we have a flat bottom and a flat top. And to do this, we need to find this point. We are going to call it the midpoint. And so what we want is to know its coordinates, so mx and my. My is pretty simple to find because it's the same value as v1y. So my is going to be equal to v1y. That's pretty simple. But mx is a little bit more tricky to find. But look at this. You can say, okay, we got the x value. I mean, let me show you this, okay? Here we can actually build some similar triangles here, which means that we can get the value of this segment, of this length. And because we know the value of v0x, if we add this length to it, we'll be able to find mx. Okay? And so this value, I'm going to call it v, I guess, over this distance, which is v2x minus v0x is equal to this. Let me use some different colors. It's equal to this length, which is v1y minus v0y divided by this distance, this length, which is v2y minus v0y. And so v, this value v, so this length here, v is equal to, so v2x minus v0x multiplied by all of this, right? And so mx, this value of mx, is going to be equal to all of this plus this value of v0x. Okay, I hope that makes sense, right? We have these three vertices. Boom, boom, boom. And we got our midpoint here. So mx, which is here, is equal to v0x, which represents this distance, plus the length we just computed, which is equal to v2x minus v0x multiplied by v1y minus v0y divided by v2y minus v0y. Okay, I hope that makes sense. I think that should not be too complicated. But maybe you're asking yourself, well, what happens if we have a triangle that looks like this? So, and you're like, oh, maybe this is going to be different. The formula is probably going to be different, you know, because mx is smaller than v0x. And you're like, well, you know, here we're adding two things together, it should be bigger. Well, actually, it's not a problem because this value is going to be negative, right? Because we're going to do, so this is v2 and v2x minus v0x, because this is smaller than v0x, this is going to be negative. So this value is going to be negative. And so we're just going to subtract something from v0x. So this formula is going to work for like these two configurations. Okay, I hope it makes sense. Okay, so once we're done, we have 4 points. So V0, V1, V2, M, and M. So now we are going to be able to build two functions, one to draw the flat bottom and one to draw the flat top. And so I'm going to kind of explain just one of them because then the principle is pretty much the same. So let's focus on drawing flat bottom. So we are going to be given 3 points. So one for the top and one for the bottom. Let's call it B1 and the other for B2. Okay. So I told you I'm going to draw line by line, which means the value of the Y is going to increment by 1 every time. 1, 1, 1. But we need to have some value of X. So X begin, I guess, and X end. And these 2 points are going to start with the top point, okay, the top vertex. And then I'm going to decrement XB and increment XD. But we need to figure out by how much we need to modify these 2 values. And how much do we modify these values depends on the slope of these 2 lines. You know, you can see T and B1 form a line or a vector, and it has some slope. And we have the same for T1 and B2. So we need to like increase XE by some value and XB by some value. But it's not necessarily going to be increased or decreased by 1. Because look at this. We're going to have 3 situations. The first one is like this one. X and Y. And we are going to have a pretty slow slope, where every time we increment Y by 1, we are going to increment X by several. So, you know, if our line is kind of pretty flat, then every time our value of X is going to increase by like several units. Like this is 1, 2, 3, 4. 1, 2, 3, 4, 4. So plus 4 every time. And so our value of X is going to start here, and then we kind of going to draw all of this, you know, this. And then when we increment Y by 1, then we are going to start here, you know, then here, then here, you know, it's like every time we have a pretty big jump of X. So the value of X is not going to increment by 1 or decrement by 1, but by a value that is bigger than 1. Then we can be in this situation where we are going to increment X by 1 every time we increase X by Y by 1. We are going to increment X by 1 every time we increment Y by 1. And then we can be in the situation where we are going to increment X by like 0.3 for every time we increment Y by 1. So we're going to kind of stay at the same position for several increment of Y. You know, it's going to look something like this. Ding, 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 ding. Right, so, okay. Here what I'm trying to like tell you is that the value we're going to increment or decrement this to value of X can be smaller, equal, or bigger than 1, you know? Can be smaller than 1, equal to 1, or bigger than 1. But we are always going to increment Y by 1. Okay. So how do we get this value? Well, it's simple. We just need to take the slope of the line. And how do we do this? Well, we subtract the X value. So take, I guess, let's use like T and B1. Okay, T and B1, and say tx minus b1x divided by b1 y minus ty, you know, because the x values goes there and y values goes that way. And this is going to give us, so this is going to be tx minus b1x. This is going to be positive, and this b1y minus ty is going to be positive, so we're going to get a value that is positive, which means we are going to start, so x beginning, and we are going to decrement this value every time we increase y. Okay, boom, 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 and this is going to shift the value of x begin. I hope this makes sense, because if it doesn't, well, I'm sorry, because I know I'm not necessarily making a very good job right now, and you know what, it's going to be worse. So hopefully you kind of have an idea about what's happening. Okay, so we got our flat bottom triangle. We got T, B1, and B2. Okay, the thing here is that I'm going to want to make a function that doesn't really want to know if B1 is on the left or on the right. Try to follow me for a second. I'm going to have a function which is called like drawFlatBottom, and that takes like T, and we know T, we know this position, this is known, we don't need to check. And then I'm going to have B1 and B2. But when we are going to give this two position, we don't actually going to know which one is on the left or on the right, okay? Which means I want to make a function that works if we swap these two around, okay? So it means that I'm going to want to perform the same operation. So we don't know the position, we don't know which one is one, but we don't care. We don't want to know. We don't want to care about this. We could, but I think it's kind of cool trick. And I'm going to initialize two variables, so x begin and x end. And then we are going to give these two variables for every line to a function that will draw a line, okay? And inside this draw line function, it will actually it will check actually which one is left and right. And so what we want to do is modify these two values every time we change line. But I want to do it in a way such that we don't need to worry about whether xb goes here or goes here. You know, I don't like this thing should work no matter where is b1. You know, b1 could be here, okay? b1 and b2 could be here. This will work in both cases. Okay, so what does this mean? It means that I want to perform the same operation on xb and xe. And here, let's say I want to decrement some values for both. So I want to perform the same operation. Because I want to decrement xb, I want some positive value. And here I want also to decrement xe, but I actually want xe to increase. So I want some negative values, because minus some values, that's a plus, okay? Here, because I want some positive value, what I do is I take tx minus b1x divided by b1y minus ty. This is going to be positive, this is going to be positive, so I will be able to decrement xb by some positive values, okay? Like this is going to give us some plus, okay? But for xe, I said I want some negative numbers. And so what I'm going to do is pretty much use a very similar formula to this one, except I'm going to do tx minus b2x, right? This is going to be this. So kind of this length, right? And this is going to be negative. So tx minus b2x divided by b2y minus ty. And this is going to give us the rate of change in this direction, I guess in this direction. It's going to give us this, but you know, the negative value of this. And by doing this, I will be able to kind of have a function that don't need to care about whether you put like b1 here or here. Okay, I hope this makes sense. Hope you're not too lost. So let me actually redo the same thing, but for like flat top. Flat top, this exact same idea. We're going to have T1 and T2, and we don't want to like do any check or care about if actually we're going to give T1 here and T2 here, okay? We don't really care. But we know that these two, T1 and T2, are at the top and B is at the bottom. Okay, we know this. And then it is going to be the exact same idea. We want to know the rate of change here and here. And we are going to initialize two variables. So x beginning and x end. And then we want to like increase xp and decrease xe. We are going to increase the y value by 1 every time, plus 1, plus 1. And the way we change the value of xp and xe can be more than 1, equal to 1, or less than 1 every time. And the way we change, oops, I kicked my camera. And so the way we get by how much we want to change xp and xe is by doing like bx minus t1x divided by by minus t1y. And this will describe how we change xp. And for xe, in the same idea, we want one to be positive and the other one to be negative. So we're going to say bx minus t2x. And because bx is smaller than this is like 3 minus 5, so this is negative, over by minus t1y. So this one will be negative, this one is going to be positive. So we're going to increment xb by this. And we're going to also increment by this. But because this is negative, then the value of xe are actually going to decrease. Okay, so let's recap. Let's recap a little bit. We are going to have some function to draw some triangle. Draw triangle. And this is going to get 3 vertices. V0, V1, V2. We are going to sort V0, V1, V2 such that V0 has the smallest y, then V1, then V2. Then we will compute the value of m, of the midpoint. Then we are going to give the flat bottom to the flat bottom function that will draw this triangle, so I guess line by line, and then another function, the flat top triangle, that will draw this triangle. Okay, hopefully that makes sense. That still makes quite some sense. And so, if I go back and recap everything we've learned since the beginning, we're actually not done. I thought I was done, but I just remember we still need to think about something else. But, you know, let's just recap. We said we are going to define our screen with the origin at the top left corner. So, and we got the x-axis and the y-axis that goes down, and the z-axis that goes inside the screen. Then we are going to have our cube, which is centered around the origin. And this cube is going to be represented by the different vertices and by some triangles. So we're going to divide our cube using some triangles. So that's how we are going to define our cube. You know, each vertex has a number, and then we split each faces by some triangles. Then we are going to rotate around each axis. So X, Y, Z. And then we are going to push this rotated cube inside the screen. Then we are going to project the different vertices into a 2D plane. Boom, boom, boom. And then we're actually going to shift. But no, before I'm going to actually scale the X and Y value of each vertices, and then I'm going to shift everything in the center of the screen. So we can actually see it, right? Then once we have actual value of each of these vertices, we're going to take our knowledge of the different triangles that these vertices are part of, and we are going to draw all of these triangles one by one. And so we have one more problem to solve, which is we are going to end up with a bunch of points, actually 8 points, which represent the 8 points of the cube. But then, well, at any time we can only see 4 of the faces, 3 of the faces of the triangle. And what we don't want to happen is to draw a face which is in the back, on front of the one we can actually see. So what we want is to only display the faces or the triangle that are facing us, and not the one that are away from us. And I guess there's different ways to do this. So what I want to use is called back face culling. The idea is that we are going to create some vectors which are perpendicular, perpendicular to each of the faces. So these vectors are called normal vectors. You know, they're normal to this 2D plane. And actually we're going to do for each triangle, I guess. So each triangle is going to get a normal vector, which is perpendicular to this plane. And we are going to use this information to know if the face is facing us. You know, if the triangle is facing us. So if this is your eye, and your eye is looking at some direction, and it's going to be the z-axis. So we can represent this vector by some 0, 0, 1. And then we are going to have some faces of the cube, like this. I guess this is my cube. And each of the triangles of this cube has some normal vector. And so what we can see is that these two normal vectors goes in opposite sense or direction than our eye vector, okay? And the faces on the triangle we can't see actually going in this same direction. Maybe I should split the word in two. Now, if a vector is going that way, and it's kind of going through the same half plane, I don't know how to call it, and goes in the same direction as our eye, then we can't actually see it. You know, it's behind. We don't see it. It's behind. But if the vector is pointing in the opposite direction, this way, then we can actually see what's going on. And it turns out there's an operation called the dot product that can give us a value for this. And so you know, I'm not going too much into the detail. I guess we will see that later. But when two vertices, let's call it U and V, are kind of facing the same like direction, then the dot product of U and V will be positive. If the two vectors go into two different directions, U and V, the dot product of U and V will be negative. And if they are perpendicular, then then the dot product of U and V will be equal to 0. And for our problem, it means that our I vector, I guess, then if the dot product is negative, we can actually see the face. If it's 0, it means that we're going to look kind of at an edge. You know, if these two vectors are going to be perpendicular, then I guess we shouldn't really display it because we're looking straight at the edge and we're not going to display or see anything. So to me, it's like if it's 0, we don't see anything. And if the face is not visible, so the dot product is going to be positive, then we should not display this face. This kind of solve our problems, which is which triangle should we display. And what we can do is for each triangle in our cube, we can define some normal vector and then do the dot product with our I vector. And I said if it's negative, then we show and we draw the triangle, otherwise we don't draw it. And so I guess the last problem we need to solve is how do we actually compute this normal vector? So like I said earlier, I'm going to give a number to each of the vertices of the cube. And then I'm going to split the different faces into triangles. And so the way I'm going to define these triangles is by, so 1, 2, 0, 1, 2, 3. So each vertex has a number. And then I'm going to form the triangle by saying, oh, I got the triangle 0, 1, 2. And I got the triangle 0, 2, 3. Here the order matters because I'm going to build some vectors using the vertices. I'm going to build, for example, for this triangle, I'm going to create the vectors 0 to 1. So 0, 1 and 0, 2. And for this triangle, I'm going to draw or create the vectors 0, 2. So 0, 2 and 0, 0, 3. You know, it's always going to be 0, 2, 0, 3, 0, 1, 0, 2. And here the order matters because what I want is I want to create a normal vector, you know, that goes out, you know, that points outside the cube, not inside. You know, I want this triangle to point outside the cube, not inside. And because I said I'm using a right-handed system, that it means that I need to do some specific operation in some very specific order. So if you're not familiar, there is an operation with vector called the cross product, which looks like a cross, you know, amazing. And if I take this vector and I call it U and V, and I do U cross product with like V, then it's going to give me a normal vector, which goes outside the cube, you know, U, it's like U, V, and then the third points up, U, V, and it's going to give us the normal vector we want. This is the cross product. And if I do V, and if I switch like V and U, do the cross product of V and U, then we'll get a normal vector that goes inside the cube. And that's not what we want. So that's where we need we need to be a bit careful about the order. This operation, this cross product, is a little bit weird, the way it is defined. So I guess if you want to know more about it, kind of look at Wikipedia. But I mean, in 3D it's like you got X, Y, Z for you, and V, let's say A, B, C, and the way you compute it, so it's a vector, the result is a vector, and it's Y times Z minus C, B, and it's like cross, and then it's like ZA minus XB, and then it's XB minus YA, something like this, I think. Okay, I spent about 2 hours on this. I think I went through everything we need to know. Hopefully it makes sense. I'm not sure, because sometimes explaining things without too much preparation is a little bit difficult. So hopefully you were able to follow everything. Now, I guess we're going to jump into writing the code. All right, so let's implement it. So recently I've been using Zig quite a lot, so I'm going to implement this in Zig. But don't worry, I will try to explain everything. I will try to write Zig that is pretty easy to understand. And if you really want me to, I will redo this in like whatever language you want. And you know what? I will even do it on Windows. But today I'm going to do it in Zig on Linux, but it's gonna be okay. So relax, if you don't know Zig, it's gonna be okay. And you know what? Actually, as an exercise, you can try to implement it yourself using the programming language you want, because I pretty much covered everything you need to know to write the code. So let's actually start. So I'm going to create a file called video.zig that will contain the contents of our program. And I'm going to start by importing the standard library using simple import. All right, and then I'm going to define the main function like this. And that's pretty much all we need to start writing some things. Okay, so we are going to print stuff on the terminal. And so the terminal can be represented as a 2D array that I'm going to call screen. So I'm creating this global variable screen, which will be a 2D array of characters. And in Zig, you represent characters using unsigned integers of 8 bits. All right. And so we are going to initialize this variable. But first we need to define its dimension. And so to do this, let me open a terminal with smaller font. And to get the size of this terminal, I can use on Linux the tput lines and tput calls command. If you're on Windows, I think you can get this information using mod con. So I got 49 lines and 206 columns. So I'm going to start by defining some constant, one for the number of columns, which is 206, and for the number of rows or lines, which is 49. And then I'm going to define my screen as a 2D array of first rows and columns. And the reason why I define it this way, which may seem a little bit weird, because this is going to be the Y and this is going to be the X, which kind of refers of like what we are kind of used to use. But the reason why I'm using it, defining it in this fashion, is because it's going to be a little bit more friendly for the memory. And so now I need to initialize it, and so this screen variable will contain everything we want to display on the screen. You know, so we are going to do some like computation, and we're going to write some character inside it that will represent our cube. But at the beginning, it's just going to be full of spaces. So in Zig, to initialize an array, the notation is a little bit weird, but it is what it is. So I'm going to define this will kind of represent some sort of like an array. So this is an array with one element, which is a space. This is like an empty screen, right? And I'm going to repeat this by the number of columns. And this will pretty much represent one row. But we don't want only one row, we want all of them, all of the rows. So this initializes a 2D array that contains only like white spaces. Now let's actually display our screen. Here what's going to happen, the logic is we are going to update the content of the screen in a loop. And so this loop, I'm going to start using a while true loop. So while this is true, it will run forever. And we are going to like update, I guess, the content of the screen. It's like it's going to be like one frame, and then we are going to display the screen. Here, because we are dealing with the terminal, we need to do a few operations. Okay, so our goal is to have the full content of the screen to be displayed on the entire content of this terminal. And every time we enter this loop, we want to start from the top left corner and display everything, every time. So one of the first things we want to do is make sure our terminal is empty. And to control the behavior of the terminal, we can use what's called as like ASCII escape sequences, or ANSI escape code. And these are like commands which can control the behavior of your terminal, like the cursor location, the color, the font, and other things. So escape codes or sequences start with the escape character, which can be represented with like all these different ways. And I'm going to use the hexadecimal representation, which is like \x1b. And then we can put the rest of the command. You know, it's like followed by the command, sometimes delimited by opening square brackets. The first thing we want to do is clear the terminal, because let's say I do something like I'm going to just print some like hello. So if you're not familiar with Zig, this is just represent like an anonymous struct, and it's used to pass some arguments to the print function, but here we don't actually have any, so this is just empty. Let me put it outside of the while loop, and if I run this, Zig run video, then you see it just print this hello, and it doesn't clear the screen. So the first thing is get rid of everything that is currently inside the terminal. And we can do this using some ANSI sequence, escape sequence. So we first need to put this escape code, and then we use an open bracket to J, capital J, and this should clear the screen. So let's try it. This clears the screen and then prints hello. But here you see hello is written kind of at this position, but what we actually want is start from the top left corner. So we actually need to use another sequence, escape sequence. So we start with the escape character, and then I can do open square bracket and capital H, and this will move the cursor at position 0, 0. And if I run this again, clear the screen, put the cursor on the top left corner, and print hello. Now, if I do this and I put hello inside the while loop, what's going to happen is it's just going to print a lot of hello. But that's not really the behavior we want, because we want to print the content of our screen variable from the top left corner. So what we're actually going to do is use the escape sequence, escape code that move the cursor on the top left corner. And so we are pretty much going to write hello over and over again at the same position. This looks like we're only writing it once, but we're actually writing it over and over again at the same position. And so that's exactly what we want, which means that we are going to pretty much need to move the cursor at the beginning every time. Now, one more thing is I want to hide the cursor because here it's clearly visible. And this can actually be a little bit annoying. So I'm going to use another sequence which hides the cursor. And it's like open square bracket, then question mark, then 25 L. And if I do this and I run it, now the cursor disappeared. But not actually disappear completely, and I can't see it again, so I'm just going to make it reappear. We actually need to use the H. So it's pretty much the same to make it disappear, but then we replace the L with the A, with the H, with the H. And it's going to reappear. Very nice. Here the problem is, it would make sense to do something like this and then make the cursor reappear and hide it at the beginning. And because this is an infinite loop and I'm breaking out of it using zig int signal, doing Control-C, this is not going to be run. And so the cursor is just never going to appear again. So if you wanted to do the thing properly, I guess we should maybe wait for some maybe listen to the signals, or maybe we should read from the input, and when we detect a certain character, we just exit the loop. But I don't actually want to deal with this, so I'm just going to ignore it. I'm just going to hide the cursor and it will never appear again, and you will have to open a new terminal, which is a little bit annoying, but I'm too lazy to deal with this. Okay, whatever. Now that we've dealt with the escape characters, escape codes, it's time to stop using this debug print and actually use the standard output. So in Zig, this is very Zig specific, so I guess you can maybe fast forward a little bit if you're not using Zig. But in Zig, I'm going to get the standard output writer. So by doing get std out and then writer. And then I'm going to write all of this in the terminal. And I'm just going to do this, and here I need to use try because this can return an error. And because it can return an error, I need to add a exclamation point here to indicate that this main function can return an error, because I'm not going to deal with error in this video. And then we need to print the content of the screen. So printing to the screen to the standard output is a pretty slow operation. So what we want to do is do it in one go. We want to print everything right away once, and we don't want to do a full loop and print character by character. This is going to be pretty slow. Unfortunately, in Zig, there's no way to there's no std out buffer print or stream, maybe stream and then flush to actually print something on the screen. I guess it's kind of part of the philosophy of the language, I guess, where if there's some kind of abstraction that is fairly simple to implement by yourself, then the language is not going to provide it to you. Which means that we need to load the content of the screen inside sort of buffer, and then we are going to give this buffer to this write all function. So I'm going to create my buffer, and my buffer needs to represent like a string, which is going to be a one-dimensional array, and its size is going to be the number of rows times the number of columns. But actually my buffer, I want my buffer to also hold some new lines. You know, at every time we write a row, I'm going to add a new line character. We don't actually need it because this should give us the size of our terminal. So it's not entirely necessary, but I've tried, and using new lines should work a little bit better. So for every rows, I'm going to add one more character for the new line character. So on Windows, maybe it's 2. I don't know, I'm not sure, because I think sometimes it's like this on Windows for a new line. Maybe try this way on Windows, and we'll see. Okay, and this is going to be undefined. And actually, this is important. I need, every time I'm going to display, so I'm going to print the content of this buffer. And I told you I want to start writing at the top left corner. So I need the space to write this sequence of character. And so this is the sequence character. So that's one character. The square bracket is another character, and then we got an H, so we need 3 more characters in this buffer. So I'm going to write 3 plus all of this. And this buffer, now this array contains enough space to write everything we want in the terminal. Alright, hope that makes sense, and I initialize it to undefined because we are going to fill it inside this while loop. The first thing we can do here is put the content of this escape sequence right here. This is to put cursor at position 0, 0. This above clear screen and hides cursor. This clears the screen and hides the cursor, and this is going to put the cursor on the top left corner. Alright, so now what we need to do is fill the rest of the buffer with the content of the screen. So let's define a function. I'm going to call display screen, and this is going to return nothing, and it's actually going to take this as a parameter, and this is of type stdfs file writer. All right, what I want to do is I have my screen variable, which is a 2D array. And each of these elements, we have like the rows. You know, it's like first we have the rows. First row, second row. And what I want is have my buffer have the first row like this. Then I'm going to put a new line character, and then the second row, and then a new line, and then the third row, etc. To do this, I'm going to create a for loop that will start from 0 to the number of rows. And this is going to give me an index. Like, think of this as like a for, like in I equals 0, I less than number of rows, and I plus plus, okay? Okay, and then what I'm going to do is create some offset. It's and this is going to give me the place in the buffer I need to write the content of the row. So I have 3 characters at the beginning of the buffer for like to move the cursor position And then I want to have the position of where I need to put the current row. So if it's a 0, then this is going to be 3, and I'm going to start at position 3 to copy the content of the screen. So I'm just going to multiply this by the number of columns plus 1 for the new line character. And then in Zig I can do mem copy and give it the buffer and give it its offset position, which is like the starting position, and then the end of the position, which will be offset plus the number of columns. So that's like the size of one row. And so in Zig, this is called a slice, which is pretty much a pointer plus a length. So I'm going to copy this row of the screen inside my buffer. All right, I hope that makes sense. And then offset plus number of columns, I'm going to add the new line character. And so now I've filled the content of my buffer with everything I want to print on the terminal. So now I can actually do a try std out, write all, and I give it my buffer. And this is going to display everything inside the screen. So here I actually need to use try because this returns an error. And when I use try in Zig, you know, if this fails, this will return an error. So I need to indicate this can return an error using the exclamation point. And then inside my while loop, I can do try display screen. I give it my std output, and this should pretty much print, I guess, nothing very visible. All right. Oh yeah. The reason why it doesn't look good is because I'm not using the correct terminal. Like this terminal is a little bit too zoomed in. So let me actually open a new terminal. Let's go in the right directory and let's run this file. And the cursor still goes crazy. What the fuck? Okay, so what's going on? What did I forget? Oh yeah, it's because it's L here. So I actually need to hide the cursor, and this is nice. That's everything I wanted. We see nothing. Amazing. All right. So during the update phase, we are going to pretty much write something on the screen inside the screen variable. So if I do like this, and I put some like character, like a star. Let's actually do like several. Let's run it here. So this should display this. All right. It's a little bit flickering though. Is that because it goes too fast? Maybe let's add some like sleep function. So I guess I got std time, maybe sleep in nanoseconds. And I'm going to put like 100 millisecond. Should be 100 million nanosecond. And if I try this, does it look better? Yeah, looks fine. We see a few stars. So let's keep going. Now, the thing is, before updating the content of the screen, we want to erase whatever we actually wrote inside of it. Because if I start putting some characters and then on the next iteration, I'm going to write all the characters, then we'll start having a lot of characters and it's going to look like shit. So we need a way to pretty much clear the screen, and the way I'm going to clear the content of this screen variables is by pretty much just putting back some white spaces. And in Zig, this is kind of a little bit cheated, so it's probably going to requires you a little bit of more effort, like not a lot, but in Zig you can do something like this. I'm just going to copy the content of the screen. I'm going to create a constant. I'm going to call it cleared screen, and it will just be an empty screen. And then I'm going to define a function called clear screen, which returns nothing, and it is going to assign screen to clear the screen. And that's it. The content of the screen will be replaced by the content of this array, which is just a lot of white space. Okay, so in other languages, you're probably going to do some like for loop or something. But in Zig, arrays have value semantics, so you can do something like this. And so at the beginning of my while loop, I'm going to clear the content of this variable. Okay, so I think we're done with the like printing stuff on the screen. I think we got all the function we need. So let's actually start showing, let's actually show the cube. Let's show some interesting stuff. Let's start thinking about the 3D cube. Okay, so I told you that we need two things to represent the cube. We need the different vertices and the triangles that define the cube. Okay. And so first we need a data structure to represent 3D points or vectors, I guess. So I'm going to define a struct. I'm going to call vec3 for 3D vectors. This is a struct, and it's going to have an x, y, and z component. And I want to give them a type of f32, so floating point 32 bits, 32 bits floating points. So actually in Zig, there's this vector type, which we could actually use to define some vectors. And what's cool about this is that you can use SIMD instructions, so single instruction, multiple data. And we could use this to speed things up, but because most languages doesn't have vectors like this, I'm not going to bother, okay? That's why I'm defining a struct, because I think most language should be able to do something like this. So now that I have a vec3 type, I'm going to define my cube. And so here I'm just going to copy paste what I already did, because it's just going to be a little bit faster. And if I show you this image again, this is going to represent the different vertices. And so I gave a number to each of the vertices, and I put like a little comment next to the actual vec3. For example, 0 is at like -1, -1, -1. The 3 here is at 1, -1, -1. And I also need, like I told you, to define the cube like triangles. And the thing is, I recorded like the previous part like 5 days ago, so I don't remember exactly what I told you on it. But I'm pretty sure I did. Told you that we need to pay a little bit attention to the order of the indices to define the triangles, because when we are going to do the backface culling, we are going to create some vectors, and the order of the vertices matters. And so the way I'm going to do, so here I've taken all the faces of the cube and I've drawn them so they are kind of facing us. And so we want the normal vectors to point like toward us. So that's why I'm going to start like 0, 1, 2. So we can define the vector 0, 1 and 0, 2. and then 0, 2, 3 to define the vectors 0, 2 and 0, 3. So the normal points toward us. And then it will be like 3, 2, 4 to do 3, 2, 3, 4 and 3, 4, 5. Okay, I hope you understood this. I'm going to define a new array, which is going to contain the cube like triangles. And the way I want to define this is I'm going to have 12 faces, and I'm going to, for all of these faces, I'm going to store an array of 3 U8. And this U8 is going to be the index inside this array, right? You know, like, okay, I didn't say it, so let me say it now. The way I define the vertices, you know, the number corresponds to its position inside this array. Okay, I hope it makes sense. This is the first element, so it has index 0, then 1 and 2, 3, 4, 5, up to 7. And so for my triangle, I'm going to define an array for each triangle, and I put the index or the indices of all the vertices of the triangle. So this is the vertex 0, then 1, then 2. And so this triangle corresponds to this triangle of the front face, right? That triangle. And so the next one is 0, 2, 3. So I copy this, and this is 0, 2, and 3. And this corresponds to the front face. So if you want, you can like try that by yourself. You can pause the video. So I'm going to copy paste the rest so we don't waste too much time. All right. And so once again, you can pause the video and check for the result, or you can check out the Git repository. You know, I'm going to like commit everything I've done. Okay. You can find the link in the description. Alright, so now that we have all the information we need to represent the cube, let's actually start thinking about how to draw the cube. To do this, I'm going to define a new function. I'm going to call drawCube. And here I realized that I haven't been consistent with the function name. And in Zig, the convention is to actually use camel case or clear screen with 2E, could be better. So camel case for function, or is that, oh man, I never remember. So in Zig, the convention is use camel case for function, title case for type name, and snake case for variable names. So let's just change this really quickly. And drawCube, okay. It should return nothing. So I'm going to define this drawCube function, and the goal is to modify the content of the screen variables to put some characters to display the different triangles of the cube. And so to be able to do this, we need to transform the different vertices, because we want to convert from this like 3D points, which are like floats, to like 2D position on the screen. So we're going to need to iterate over the cube triangles, and using this syntax, I'm going to extract element by element of this array. And for each of these triangles, these are actually made of like three elements, so I can, I guess, do a simple for loop from 0 to 3 and have a I value. And what I want to do is modify, so the cube vertices I. But I'm not actually going to modify that variable right away. I'm going to make a copy of it. So let's create a vertex variable, triangle, right, like this. And so we are going to transform this variable. So I'm going to like rotate it, going to like push it into the screen, and I'm going to scale it. And I'm going to do this for each of the vertices of this triangle. And once I have the 3 transform vertices, so I guess I should like do something like define an array of like transformed vertices. And I'm going to have 3 vec3 be like undefined at the beginning. And I guess I can just do transform.I. I'm going to take a copy of the original vertex. I'm going to rotate it, push it, scale it. And once it is transformed, I'm going to check if this like triangle should be like displayed. So this is going to be like the back face culling part. If this triangle is not visible, I guess I'm just going to continue early and go to the next triangle. Otherwise, if it's like facing us and we need to display it, then I'm actually going to project this 3D point into some 2D point, and then I'm going to draw the triangle. Let's actually start drawing the triangle. So I'm going to define a function called drawTriangle, and I'm going to give it 3 points, so v0, v1, v2, and this is not going to return anything. And if you remember what I said, the first step is to sort the different points by ascending y, so from the lowest value of y to the biggest. Then we need actually to find the midpoint, and then we need to draw the flat bottom triangle, and then draw the flat top triangle. You know, like we sort the vertices, then we kind of split this triangle in 2, and then we draw each individual triangle. Here, let's think about the data type we are dealing with. At this point, when we draw triangles, we actually need some 2D points. So we'll have a project function that can take a vec3 and then need to return the vec2. So let's define a vec2 type, which will pretty much be the same as the vec3, except we remove the z component. Here, it would make sense to use an unsigned int, which is use size for several reasons. One is because whenever you access like a value inside an array, you do array like I equal like 2, for example. The I need to be of type useSize. You know, useSize is like the type of indices, which is an unsigned integer, which depends on your architecture. So if you're on a 64-bit architecture, this is going to be 64 bits. And if you're on a 32-bit architecture, this is going to be 32 bits. But Zig requires us to be very explicit with like data type and casting and conversions. And if we use floating points, it's just going to make our life much easier. I'm just going to use 32 bits floating point to represent our 2D point, okay? Because it's going to make our life easier. So to draw a triangle, we're going to get 3, so vec2. And I kind of want to go deep, so I'm going to just kind of ignore this function for now, and I'm going to start focusing on one of these 2 functions. So let's actually start with drawFlatBottom. Okay, we are going to get one vertex, which is going to be at the top, and it's going to be a vec2, and then we have two bottom points. So let's call it v0 and b0 and b1 for the other one. And so let's recall what I said. So we are not going to check which one is on the left or on the right. You know, we're just going to do the computation such that b0 and b1 are on like either side and it doesn't matter. So here we have our drawFlatBottom. So this will look like something like this. So we got t, b0, b1, and we are going to have like two variables called xb and xe and xe, and we are going to give this value at the beginning, the value of tx, and then we want to like decrement xb and increment xe by some value, and the value will depend of the slope of each of these two like side. And every time we have some value of xb and xe, we are going to draw line by line like this. And we are going to draw so line by line, and so we're going to start with the value of ty and do +1 every time until we reach like b1y or b0y, because these 2 points are on the same line, so we can take either. And so before implementing any of this, I want to implement the function that actually draws some lines. So for now, let's just ignore the parameters, and let's actually implement the like drawScanLine. And this needs 3 arguments. We need y, which will be a usize, x0, which will also be a usize, and a x1 be a usize. And this is not going to return anything. Here I actually want to know which of these two positions, x0 and x1, are left or right. So I'm going to define 2 variables, one left, and I'm going to assign it to x0 and right to x1. But if I was wrong, so if actually left is bigger than right, then I'm going to switch this such that left is x1 and right is x0. Right. And then I can just print the line. And I'm just need to iterate from left to right +1. And this is going to give me the x position. And then I can fill my screen with the y and x coordinates with some symbol, like a star. But here I actually want to display a different character for each face of the cube. So I'm going to give this function a new argument called symbol, which will be of type u8 or character. And I'm going to modify the screen to contain this symbol. Let's try this. So if I try to do drawScanLine, and let's say at line number 4 from 20 to 100, and I'm going to show the letter O, and let's draw a different line at line 20 from 25 to 150, and I'm going to print the letter A. Let's try this. And we have some lines. Very well. Woo! All right, I'm going to try and not be so boring. Big lines, you know, you just draw this. Wow, so good. Amazing. So now we got some lines. We can actually start drawing some triangles. So let's actually implement drawFlatBottom. If I take this little drawing I did, we need two variables, so xb, xa. So let's start doing this. We need some variable xb, which is going to be equal to t.x, and xe, which is also going to be equal to tx. And we are going to have some loop that's going to pretty much go from ty to tb0y plus 1, I guess. And this is going to give us our y value. And then we are going to update values of xb and xe. And then we are going to draw our scanline. So y, xb, xe, and then we're actually going to need some symbol. So let's use a star for now, but we are going to define an argument later, and we're going to change that symbol for every like triangle, I guess. But let's just draw some stars for now. All right, so we need to do quite a lot of work. One is we actually want some usize value, right? We want y, x0, x1 to be usize, not unsigned integers. And here our vec2 actually holds floating points number. So we are not going to be able to do this, I don't think so. Maybe we can, but I'm not going to really bet on it. So let's define some constant to hold the start, which are going to be usize. So the y start and y end, or maybe to be consistent, y b and ye, and this is going to cast, so int from float t.y, and this is going to be, we're going to cast an int from a float, which is b0 y. All right. And let's actually do the +1 right here. And then I can just do my for loop from yb to ye. Right, so that's pretty good. Now here xb and xe, this function need to actually be floating point number, because we are not necessarily going to increase or decrease these two values by some integers. You know, this can be below 1, this can be smaller than 1. So, I mean, we are going to increment or decrement by some value that it can be below than 1. So we are going to keep these two values as floating point numbers. But inside here, I'm just going to convert it to int. And I'm also going to round them. You know, first I round them and then I convert them to integers. Now let's actually get by how much we need to decrement these two values. And so if you remember what I told you previously, to know by how much I need to like decrease the value of xb and increase the value of xe. I need to compute the slope. And I'm going to decrement both xb and xe. So I'm calling xtech1, which is of type f32, which is equal to tx minus b0x divided by b0y minus ty. And we are going to do the same. I guess I should call it 0 and 1. And here I'm going to change b0 to b1. Hopefully that makes sense. And so we are going to draw our line. And every time we increment y by 1, I'm going to decrement xb by x dec 0 and xe by x decrement 1. And this should work. So I think I haven't made any mistakes. So let's actually try this. And so let's try to draw some like flat bottom. And we need some vec2 on the top. Let's try to define the x at the center, which is about 100. And y, let's give it position 5, let's say 5. All right. And then the bottom, we need 2 other points. Let's put x at 10 and y at like 30. And then let's put x at like 200, I guess. And y need to be at the same height, or the same y component. So let's actually try this. Let's remove the scan line. So let's try this, and it works. And let's actually check that if I swap these two, now this one is actually, the order of these 2 bottom points are like swapped. If I rerun it, it still works perfectly fine. We are making like very good progress. So let's actually do the same thing, but for flat top. So I'm just going to copy everything, flat top, and this time I'm going to have 2 top positions, so T0 and T1, and 1 bottom point. And so the beginning point XB will be T0x, and T1x will be the end, XE. Then I will actually this time increment, and increment will be, here will be the bottom, and this will be replace T and T and T and T. This is actually going to be the bottom point, T1 and T2. Oops, T0 and T1, sorry. This is going to be like this, that way, boom, 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 like T0, T1. Whoops, and then I'm going to increment T0, decrement T1, and by doing Bx minus T0x, this will be positive, and I divide it by By minus T0y. So I got a positive value, and I can increment, I guess, xb by this value. And then if I increment xe to plus equal, I want a negative value. And by doing bx minus t1x, this is negative. X minus t1x, this is negative. Over by minus t1y. And so this time I'm going to actually increment these two values. And the starting position and ending position of y will be actually so t0 or t1y, and the end position will be bottom y plus 1. And I think that's okay. So let's try this flat top, and I said I was going to have top 1, so I'm going to put you know what, let's put I guess t1 here, and then t2, let's maybe put like 200, 5 y position. So these are the two top points, and then the bottom will be x in the middle, y at 30. So let's try this. And we have a flat top triangle. Amazing. Amazing, amazing, amazing. All right, so now that we have these two functions, drawFlatBottom and drawFlatTop, I think it's time to draw some regular triangles. So the first step is to sort these 3 points. Now we are going to have 3 points at arbitrary positions, and we want to have v0 here, then v1, then v2. And this order matters so that we can actually find the midpoint, and then we can give these 3 points to flat bottom and the 3 points to flat top, and we will be able to draw this triangle. Okay, so here I actually want, I'm going to modify these names. I'm going to call vec0, vec1, and vec2. And I'm going to create the variable v0, which is equal to vec0. And I'm going to do the same for v1 and v2. And then I'm going to do a sort of like simple bubble sort. And to do this, I just need to first check if v0 and v1, I need to check if v0y is greater than v1y, then I can swap v0 and v1. You know, I can say actually v0 should actually take the content of vec1, and v1 should take the content of vec0. So now, after this, we know that v1y is greater than v0y. And so now we need to check if v1y is greater than v2y. Then we need to swap v1 and v2. So here I'm going to create a temp variable to store the content of v2, and then I'm going to do v2 is equal to v1 and v1 is equal to tmp. And so now we know v2y is greater than v1y, but we don't know if v1y is greater than v0y. Because here, if we actually swap v1 and v2, it means that v1 is greater than both v0 and like v2, but we don't know that the old value of v2, we don't know if the old value of v2 is greater or smaller than v0. So we pretty much need to copy paste this, and then I'm going to swap the content of v0 and v1 if v1 is actually smaller than v0. So v0, I guess, v0 and v1. Right, like this. And now we know that the vertices are sorted by ascending y. And now actually what we can do is kind of take a shortcut, because if v2y is equal to v1y, y, then we can just draw a flat bottom. And so the top is v0, then v1, and then v2. And we can just return only. And if v0 y is equal to v1 y, then we can draw a flat top. So got v0, v1, and v2. Okay, so here we have floating point numbers, and you shouldn't compare floating point value like this. That's not good. But I'm kind of lazy, and this will work fine, and I'm going to do something in the project function that should not be a problem, I think. But yeah, so that's not how you should compare floating point numbers, but like if you want to do it right, it's a little bit annoying, and it should still work fine because I'm going to round these two numbers in the project function. So, and I think it should be fine, but floating point sometimes are a little bit weird. So yeah, maybe I should do things differently. Okay, actually tell me if you know more about this than I do. Tell me. All right. So now we can just return early when we draw a flat top like this, and then if the values of v0, v1, and v2 are different, we need to find the midpoint. So let's define our midpoint, which is going to be a vec2, and it's going to have an x value and a y value. And the y value is it's v1y, but the midpoint x is, if you remember what we said, we have like these two triangles. So we need to compute this length. So this divided by this is equal to this on this, right? And then let's actually call them A, B, C, D. So A, B. I'm really taking the worst fucking colors. So A over B is equal to C over D. And then MX will be equal to, so this is V1X. This point is B0X plus, so B times C over D. And so this is going to be equal to V0X plus, so V2X minus V0X multiplied by V1Y minus V0Y divided by V2Y minus V0Y. And so this should give us the value we want for the midpoint. And now we can actually draw our two triangles. So we have the drawFlatBottom, which will be V0, and then V1, and then midpoint, and drawFlatTop, B, V1, midpoint, and V2. All right, so let's try to draw a triangle, and let's see if that works. So let's draw a triangle. And I'm going to give it a first x at position x10, y5, why not? Then an x at 150, position like 15, and then one at position 70. And y at position 35. Or 34, I guess. Let's try this. Hopefully it's going to work. And it seems like it's working. Very nice. Very, very nice. All right. So now we got everything we need to draw a triangle. So let's actually focus on drawing a cube. Everything's going great, so let's keep going. Let's go back to the 3D world where we have a cube in 3D. So the first thing we want to do actually is to rotate it. But I think I'm going to do that a little bit later. Instead, I'm going to push all of the vertices inside the screen. So I'm going to take my transform vertex I, and I'm going to push it inside the screen. So I'm going to increase the Z component by 8. Because I tried like different values and 8 worked pretty well for my terminal. So maybe you will have to like modify a little bit the values, but 8 worked pretty well for me. And then I need to scale it. You know, for now, our cube is pretty small. It only has value from -1 to 1. So it pretty much has a value of like 2. It's a 2 by 2 by 2. But if we keep this value, this is going to be very small and we're only going to see like 1 or 2 characters. So we need to increase it and make it bigger. And here I just want to increase the value of X and Y, not Z, because otherwise it will really make the cube very small. Hope you remember what I said. And I'm actually not going to scale X and Y by the same factor because I would say the height of a character is bigger than its width. So I'm actually going to increase the width or the X a little bit more. On my terminal, I figured out that scaling the X axis 3 times more than the Y axis looks pretty good. So maybe on your terminal it's going to scale it a little bit differently. But here what I'm going to do is I'm going to scale so the Y axis. And to scale it, I'm just multiplying it by some like scale factor. So let's define a called scale, and I'm going to use 60. And for the x-axis, I'm going to do scale times 3. So now that we've transformed all the vertices in my cube, well, we need to figure out if this triangle should be displayed. Then we project the point and then we draw the triangle. But I want to display some things, so I'm just going to skip a few things, and I'm going to first start by projecting all the points and then draw the triangle. So I'm just skipping this, and rotation for now, we'll do it later. Hopefully I will be able to draw something on the screen that doesn't look too bad. Okay, so let's actually project our points from 3D to 2D. I'm going to define a project function that takes a vec3 as input and return a vec2. And to do this, it's going to be pretty simple. We're going to return a vec2, and the x coordinate will be equal to vx divided by vy, and the y will be vy divided by vz. Yeah, it's vz, sorry, by vz. But here it's not actually enough if you want to show them to the screen. So what I'm going to do, and I'm doing it right away here, is I'm going to push the different vertices toward the middle of the screen. So for the x, I'm going to add the number of columns divided by 2. I'm kind of pushing everything at the center, and I'm doing the same with the rows divided by 2. And here because I actually want to have like position that can correspond to real position on the screen. I'm going to round these values. All right, I'm rounding this. All right, so now that we have this function, we can project the transform vertices into like 2D points. Okay, I'm just going to delete this comment and I'm going to create a new array of like projected points. So it's going to be an array that contains 3 points of vec2. And I'm just, yeah, and it's undefined. All right, so let's loop through the different transform vertices. So from 0 to 3, I'm going to project each of these transform vertices. And I'm going to store the result into this project points array. Projected points. And now that we have all we need, we can draw the triangle. And we can do projected point 0. And I can repeat this. Maybe using 3 variables will be even easier to do this, but whatever. Well, let's actually try this, right? Let's try this. Call drawCube function. And I have no idea what is going to happen, but it draw a square. Amazing. That's really, really cool. Okay, so before going a little bit further, I want to make sure that I'm not going to only display stars. You know, like in drawFlatTop and drawFlatBottom, I gave the star symbol to only draw some stars. So let's remove this star and let's actually use a symbol. And I'm going to add some symbol argument or parameter. I always forget which one is which. I guess these are these are parameters, right? Because arguments are the actual value and the parameters are the placeholder. Okay. So I'm adding some parameters. Symbol, and we're going to give symbol, which means that we need to give some symbols to these 2 functions. And we need also to create a new parameter to draw a triangle, which is also a symbol, which is a character, so that we are going to be able to draw our faces with different characters. And so inside drawCube, I'm going to want to give some like symbol to my drawTriangle function. Okay, and to do this, I think the simplest solution is to define a symbol constant, which is going to be a string. And I'm going to really do something very simple and basic. So I'm going to give 1 character for each triangle. And because my triangles come like in pairs, I'm going to give the same symbol for each triangle. But you know what? Let's give different symbols for now. Let's try this. Like A, B, C, D, E, F, G, H, I, J, K, L. So that's 12 symbols. And actually, I'm going to... Okay, this is a little bit dank. That's Zig specific, okay? In Zig, you can iterate over several things at the same time. So here I'm going to define a range, 0 from whatever the length of this is. So this is pretty much going to be 12. So this is going to do from 0 to 12, and I'm going to store this into a variable, which will be an index I called s, which will allow us to choose a symbol in this string. And so in my drawTriangle, I can do symbol and s, and this will take whatever symbol at this position is. All right, so if I try this, it doesn't work because I'm missing some argument somewhere. Line 127, 127. I am missing symbol here and here. Oh, I made a mistake. And yeah, this looks pretty awful, but this, I think this is working. Is this working? Yeah. Here, I think what's happening is that I'm kind of drawing all the faces. So this, the F is like the back face with the E. And then the D and C are like the right faces, the right face. H and G is the left face. K and L is like the bottom. I and J is the top. Right, I guess that looks kind of right. So now we only have to rotate it. And then we will just do the back face culling and just ignore the faces that are away from us. Yeah, we're doing good progress, you know? It's not as painful as I thought it was going to be. You know, this is kind of the first time I record a video this way. So hopefully it's not too painful and I'm not too boring and you're still able to follow it. Hopefully, I don't know. I'm not sure. But I hope it's gonna be great. But this is, I mean, it's not going to be great. You know, it's my first time. But I'm trying. And it's getting late. So I need to hurry to finish this up. And need to finish things up. Holy shit, man, I can't speak English. English is difficult, okay? I'm trying my best. English is difficult. I'm trying my best. I'm trying my best. All right. Okay, so. Okay, it's starting to look like something. So let's do rotations. Okay, rotations. Rotations. That's kind of the first thing we want to do is rotate all of our vertices before doing anything else, before pushing them, because we're going to rotate around the different axes in 3D. So what I'm going to do is define some function. So rotate around X, and I'm going to give it the, I guess, transform vertices I, position I, and I'm going to give it some rotation angle. I'm going to call it Rx, and I'm going to do the same for Y, Y and Z. And I guess this function is going to transform this variable. So I'm going to take a pointer. So let's start with 1, and which one makes sense. Our screen is like X and Y. Z is inside. Let's start by rotating around Y. Just going to comment this and this. So I'm defining this rotate around Y, and this is going to take some vec3 and some rotation angle in radians, which is F32, I think. It's not going to return anything, but it's going to... Actually, it's kind of annoying to... Now I'm thinking a little bit more. I think it's a little bit annoying to modify the value. So what I'm actually going to do is have this function return a new value, a modified value. like this. Okay, so let's forget about this. This rotate around y is going to create a new point. Okay, this is going to be simpler. So I'm lazy, so I'm just going to go to Wikipedia and type rotation matrix, and I'm going to look at these three matrices, and I'm just going to use this. So if you don't know how to use this, let me show you very quickly. So you have this rotation matrix, and you have your like vector, which is x, y, z. And the way you do this is by multiplying your matrix with your vector. And the way you do this is you multiply x with like this value, then you add plus y multiply time like 0, and then z multiply by sine of theta. So this you will add the value x time cosine of theta plus, I guess, sine of theta times z. And then we are going to multiply this by this row. So we are going to end up with just y. And then we multiply, we pretty much do the dot product of this column with this row. And then for the z value, we're going to get minus sine of theta times x plus y times cos of theta. And here I've been very inconsistent in where I've put x and z and y. That's because I'm kind of a moron and don't do this. Okay, hopefully that's clear. That's if you're lucky. Okay, if you survived my very bad explanation, then good for you. All right, so now that you're very satisfied by this explanation, I'm going to just, inside this function, rotate around y. I'm going to return a vec3, which is going to have the x equal to what we said, so cos sine of the like rotation angle in radian time v of x plus the sinus of this rotation angle in radian time vc. And for y, it's going to be exactly the same value. And for z, it's going to be minus sine of the rotation angle time vx plus the cosine of the rotation angle time bz. All right. And these are not semicolons, but commas. All right. And that should be good for rotating around y. Why? Here, I want to rotate by some value, and this value will be a parameter of the drawCube function. And so I'm going to define 3 parameters, one to rotate around each axis. So Rx will be of type F32, and we're going to get, and so I want 3 of these, one for Z and one for Y. And then we are going to pretty much repeat this to rotate around X, to rotate around Z, and we're going to have RZ, RX. This is not implemented yet, so I'm just going to ignore RX and RZ for now. All right, and here I'm going to give to my function some value of Rx, Ry, and Rz. So I'm going to give some value, some rotation value to my drawCube function. Okay, so I'm going to give some like rotation angle to my drawCube function. So let's actually define this Rx, and I'm going to start with some 0 rotation. So let's do this for Y and Z2. And so I'm going to update these 3 values at the end of my while loop. I know I said like update at the beginning, but whatever. Rx, I'm just going to set it to 0, Z to 0 for now, and Ry will actually take some value. And so what is the value? So what value can these angles can be? Well, it's in radians, so to have a full rotation, we need a value of 2 pi max. So I'm going to increment the value of the rotation until it reaches like 2 pi. So I'm just going to do plus some value modulo 2 pi. So it's in this range. And in Zig, it looks something like this. I take the modulo of whatever the previous value of Ry was, plus, let's try 0.1, and so the modulo of 2 times pi. Should we try this? Yes, let's try this. All right. Okay, so I forgot to change this because I'm actually returning vec3. Let's try it, and that looks like something is rotating. So it seems like something's happening. Seems okay. Okay, so actually I'm going to modify the symbol I've been using, this one, or something a little bit better that looks a little bit better. Boom. I think it should look a little bit better. But yeah, not sure. So now the triangle of the same face share the same character. Okay, that's one thing. I use this. You can use whatever you want. Doesn't really matter for this video. Okay, so now I can actually repeat the same thing for rotation around X and Z. So I'm just going to copy, paste this rotate around Y twice, and I'm going to do rotate around Z and X. And then it's kind of the same principle. You know, if you want to do it by yourself, you look at the Wikipedia page, you look at the matrices, you can compute, you know, do the multiplication, the matrix multiplication. And actually, let me try to do this. So around Z, I need to take that one around Z. So I need to multiply for the X axis, I need to multiply Vx by cos of theta, then it's going to be minus sine of the rotation angle multiplied by Vy. For the Y component, we are going to have sine of the rotation angle multiplied by Vx plus cos of the angle times Vy. And for the Z component, we're just going to give it the original Vz. And around X, we're going to do, it looks a lot like around Z. I'm going to copy this, paste it there, and this X will be Vx, Y will be this, but Vy, Vz, and then Vz, Vy for the Z component, Z component or Z component. And I think I'm good for this. And I can remove this, and we should start seeing things rotating. Oh yeah, I forgot to modify this Rx and Rz. I'm just going to copy this 3 times. It's going to be z and then x, and then I modify rx and rz, and let's do this again. And now it starts rotating in the three dimension, 3 axis. But as you can see, it looks a little bit weird because we are actually displaying like the faces, the back faces. So we need to stop displaying the back faces. Yeah, we are actually almost done. We just need to not display the faces that are away from us. And so, if you remember what we need to do, one is to compute some normal vector of the triangle. So I need to define like 3 vectors, or 1. I need to define 2 vectors, v0, 1 and v0, 2. You know, if you remember the picture I showed you, when I have a triangle like this, like 0, 1, 2, I want to define 2 vectors, 0, 1 and 0, 2. Once I have these 2 vectors, I'm going to do the cross product of 0, 1 and 0, 2 to get the normal vector. And then I will do the dot product between this vector and some like arbitrary vector that points inside the screen, you know. So first let's define these 2 vectors. So these are going to be some vec3, and the x value is going to be the transform vertices at position 1 minus the vertex at index 0. Well, of course I need to do like x and x, alright. And I do pretty much the same for all dimension, like y and z. Like I hope this makes sense. You know, it's like you just apply the difference of the different coordinates of each of the points. And I'm going to do pretty much the same thing, but I'm going to use the second, I guess in the third point of the triangle. And so now that we have these 2 vectors, we want to get the normal vector. And to do this, I'm going to define a cross product function, and I'm going to give it these 2 vectors, v0, 1, v0, 2, and it's going to return the normal vector. So let's define this function, cross product. You'll take vector a, which is a vec3, and b, which is also a vec3, and it will return a vec3. So we are returning the cross product, which is a vec3, and will look like this. So the x component is equal to a y times bz minus a z times b y. Then for the y component, it will be a z times bx minus a x times bz, and for z it will be equal to a x times by minus a y times by. So that's the cross product. Amazing. And so we want to compare this normal vector with some sort of like camera vector. And I'm going to define this camera vector here, camera vector, and this is going to be a vec3, and the x will be 0, the y is 0, and the z component will be 1. I don't remember. What did I told you? Was it like z 1 or minus 1? I don't know. I'm just going to pretend that we are like, that's kind of like our eyes or our camera is looking at the screen in this direction. So the Z goes inside the screen. So this like vector can be represented by like 0, 0, 1. That's what I've just written. Hopefully that makes sense. So now we need to do the dot product. And so if the normal vector and the camera vector, so normal vector and camera vector, I guess so if we do the dot product of these two vectors and the result is negative, then we will display the triangle. Otherwise, if it's like, I guess equal to 0 or above 0, if it's positive, then we will not display the triangle. So let's define a new function that I will call dot product. And it's taking, I guess, to vec3, and then I'll return the value of the dot product, which will be f32. And so it's ax times bx plus ay times by plus az times bz. And so now what I can do is, so the result of doing the dot product is equal, so the result of the dot product of the camera v and the normal vector. So I compute the dot product, and if res, I guess it's not very that's not a really good name, but res dot prod, let's call it res dot prod above or equal to, man, I can't find the equal sign. So if the result of the dot product is, I mean, I guess I could just do this, like, holy shit. Sometimes I'm struggling. If this result is equal to 0 or above 0, then I can just continue and skip all of this. And I think it's good. I think it's enough. So let's try this. And it doesn't work. All right. Very, very nice. What did I do? What did I do wrong? Oh man, I thought I was done. Let's check the cross product. Am I good with the cross product? A, Y, B, Z minus A, Z, B, Y, A, X, B, Z, B, X, A, Z, A, X, B, Y, B, Y, oh. Ugh. Okay. Is this better? It works. Okay. Well, that was pretty eventful, and we are almost done. Yeah. You thought we were done? What? You think this is good enough? I mean, what the fuck? I want to do one last thing, okay? One last thing. Here we're doing something something not quite as good as it could be, okay? Let's just say that. Yeah, I'm just, sleeping for some 100 millisecond, and then I update the value. So the one frame will last for 100 millisecond, and it works pretty well on my computer. Works okay. But maybe you have a slower computer or a faster computer. And doing this is just going to be way slower or way faster, and it will look very differently. And so we need to start talking about the time it takes to display a frame. And so, you know, we want to kind of display frame by frame, and we want the time, the duration of each frame to be pretty much the same. And so what we want to do is, you know, we are going to spend some time, like do all the computation, and then we'll have to wait some time. You know, we are going to do like some updates, and once we will be done, we want to sleep some time. But sometimes this update will take more time or less time. So we need to wait a different amount of time. Okay. What we want to know is how much time we want to wait for each frame. And this will also affect the animation we want to draw. Because what actually can happen is, and I barely remember what I want to say, so bear with me. The amount of time we need to compute all the calculation kind of affect how much frame we can display per second. You know, the frame per second, the FPS, kind of depends on how fast our computer is. And, you know, maybe you have like some slow, maybe file system or something. So printing to the standard output is like very slow. And maybe you can't have as many frames as me, or maybe you get way more. And so what we don't want is to have some, like, let's say the blue boxes here are like the kind of the target duration, you know, target duration. But let's say we have a very slow computer and the time it takes is like bigger than the blue box. So what we need to do is, I guess, increase the size of our blue box such that we have time to do all the computation. You know, and we want to kind of have the same time for each frame. So the number of frame will decrease and go down. And because it goes down, we need to change by how much our animation, like we need to change kind of the speed of our animation. And here in our problem, our animation is like the rotation. So if we slow down, if we reduce the number of FPS, then there will be less frame. So we are going to want to rotate more. You know, we want to have like kind of smooth and consistent animation speed. So for example, if I have my, let's say my cube, which is not like this, and I want it to be this way, like rotating that way, at the end of, like, let's say this time interval. If I have like more FPS, like this, then I will need to rotate a little bit every frame. But if I have less frame, if I have like this, boom, for the orange, I will need to rotate more every time. And so to make this simple, because this video is getting very, very long, what we need to do is kind of multiply like the speed of our like rotation, I guess, by some value called delta time. And this delta time corresponds to kind of the duration of your like blue box. If you want to know more, like, you just watch all the videos, because it's getting late and I'm just trying to finish this video. Okay, I'm sorry. What I wanted to do is kind of introduce this idea of a delta time, and I'm going to use kind of a similar idea to what RealLib is doing. You probably heard about RealLib. And there's a good chance, maybe not. But there's this relib, which is a library to like build some like games or to draw things on your screen. And the way relib works, it has a kind of a set target FPS function. And you give him some FPS value you want to reach, okay? And then it will kind of try to make your game run at that like target FPS. When you have some like number X, let's say you have 60 FPS, then your delta time or your target delta time will be equal to 1/60. So 1 second divided by 60, which is equal to 1 divided by 60, which is equal to like about like 16 milliseconds, which means your like blue box is going to be 16 milliseconds every time. All right, this is not very well done because I didn't really thought too much about it. So I'm going to have this target delta time in nanosecond variable, and I'm going to give it, I guess, if I want 60 FPS, so 16 millisecond, and then it's only like 666. 667. That's kind of my target delta time will be initialized to like 60 FPS pretty much. And if I want to change this, I will call this function and I will modify like the target delta time in nanosecond. And what I will do is pretty much take the FPS and I need to do like 1 divided by FPS, except that I want nanosecond, and this will be like kind of second. So I need to do this pretty crazy thing in Zig, which is I take 1 billion, so this is 1 billion, and I need to tell that this is of type I, so integer 128 bits, and I want to divide this by the number of FPS. And this is going to give me the target delta time in nanosecond. And I'm also going to use this function as a way to kind of initialize the first kind of duration, like how long did it take me to compute and like draw and like do all of this, right? Like how long does it take me to do like one iteration of this loop? And so I will kind of define this function. I'm going to call like previous like time in nanosecond that it took me. Like this is not very good, okay? Like I'm gonna be honest, what I'm doing right now is not very good, but I just kind of want to talk to you about it. And I'm kind of in a rush, so maybe I should stop, but you know what, I want to commit. I'm committing. One of the first thing I'm going to do is actually set target FPS, and I'm going to say, you know what, actually, I want 100 FPS. You know what, I got a 240 monitor, so I got 240 Hertz. And this will say, oh, this is kind of the beginning of my frame, you know, that's kind of the beginning. And it sets how long we want the frame to be. And then at each iteration, I'm going to want to get the delta time. Like I want to know how long it took me to like compute all this thing. And so I'm creating a new function called get delta time f32, and then it will take the time now, time, timestamp, and then I'll compute the actual delta t in nanosecond, which is equal to now minus the previous time. And then I'm going to sleep for the duration it took me to like do the computation. So you know, it's the thing is like I got this is like kind of the previous time, okay? Then I'm going to do some computation. Then I'm gonna kind of call the deltaTime function, and it's going to compute how long this took, and then I'm going to sleep for the rest of like the actual deltaTime, like by the duration of the blue box, the duration of one frame, you know? So this is going to like display something, and then it will start again. We compute, get the deltaTime, we wait, and this should give us some pretty consistent animation. I'm not a game developer, okay? This is what it shows, okay? And after I'm done with this, I can actually modify this to be now. And so if sleep time is actually above 0, because maybe we are very slow, then I will sleep time. Otherwise, I'm just going to return as f32 float from int multiply f32 1e. Okay, you know what? I should have just quit. Maybe I will redo this in a different video. Yeah, that's probably better. I mean, what am I doing? Just return this already. Okay, and so then if I actually inside this, and I get the deltaTime, which will give us how long is a frame, and will sleep until the next frame. I mean, the idea is to know how long the previous frame was. And so most of the time, this should pretty much give us the same result. Always, because, you know, this function like deltaTime is probably, it should give us, you know, the value of the blue box, because most of the time all the computation happens within this range. And this deltaTime function will also sleep until the end of the frame. So we know that we spent like this amount of time for each frame. But if our computer is not powerful enough, and maybe we'll do more, then our blue box or the function is going to return the actual time it took us to do this, and it's not going to sleep at all. And because this time is going to be bigger, we are going to rotate more, because we're kind of late. We are late. If we had like more frame, we will move less and it will be smoother. But if we are like late and it took more time, that we need to rotate more. So we're actually going to use this value, and we're going to multiply by how much we rotate by the deltaTime. You know, we are going to rotate how much we're rotating by deltaTime. And so if I try this again, I need to get rid of this. And I need to increase by how much I'm rotating. I think I put like 808. And then this looks a little bit slow, but I guess it's okay. And here, if I decrease the number of FPS, for example, if I put like 10, actually let me do this, and I'm going to let this one run. I'm going to open a new terminal. And so if I modify it and I put like 10 FPS, zig run video. Like this one should move a little bit more or faster. Like this one moves more every frame. they kind of end up at the same position. All right, so that was something. Okay, let's actually put 60 back. This probably didn't made much sense because I did a very bad job at describing what deltaTime is. But, you know, we end up with a satisfying result, I think. I think it's still pretty good. We did a pretty good job. It definitely took us some time. Wasn't very easy. It wasn't that easy. But we did it. I mean, if you actually watched this video, like, holy shit. Like, holy. Thank you. And you are very patient, I guess. But yeah, I made this video. It was not easy to make. It took me a lot of time. And it was a little bit of a struggle. And if you somehow want more, you can subscribe and tell me in the comment. And I will try to do more like this. It was still pretty fun to do. So I hope I will do more, and maybe I will see you again. Never know. All right.